On the GED Science test, you may have to determine the atomic structure or what an atom looks like for a certain element. So let's see. Helium is a chemical element with atomic number 2. This indicates that it contains 2 protons, 2 electrons, and typically 2 neutrons. Which diagram correctly shows the atomic structure of helium? Well, to start, it has 2 protons. Those are always going to be positively charged. You could remember that because it starts with a P for positive. These are always going to be on the inside or the nucleus of the atom. So which of these could it be? Could be the first one, the second one, not the third one that has them on the outside, so that's not right. Or it could be the last one, that's in the nucleus there. Alrighty, next it's got 2 electrons. These are always going to be negatively charged, and those are in orbit around the outside of the nucleus. But the only one that has that correct is option B, electrons on the outside, protons on the inside, so this is our final answer, and this is the correct atomic structure of helium here. And finally, it does have 2 neutrons. Now you might think, well, wait a minute, it starts with an N, it should probably be negative. But when you see neutron, think neutral. It's like neutral in your car. Your car is not going forwards or backwards, it's just sitting there. So neutral has no charge. And they're also going to go on the inside or the nucleus of the atom. So that's it. Protons, neutrons on the inside, electrons on the outside, and then you can identify the atomic structure for any element here. Okay, let's keep going. For this problem, they're going to teach us a concept here and then ask us to apply it in the question. The diagram above shows 3 isotopes of hydrogen with isotope notation. So we know that these are isotopes of hydrogen, and the thing underneath, they're written in isotope notation, here, here, and here. So we'll break those down in a second. Next, each has the same number of protons. Let's pause there. We know protons are positive, P, so this one has 1, 1, and 1. They do all have the same number of protons, but they have a different number of neutrons. Let's highlight that. We know neutrons are neutral and they're in the middle. This one has no neutrons. This has 1 and this has 2. So that is true, they have a different number each. Finally, if lithium has an isotope of 3,7Li, then what properties does it have? Basically, we need to know what is this notation or isotope notation telling us about lithium. In other words, what properties does it have? But looking at the answers, we basically want to know how many protons and how many neutrons does it have if it's written this way. Let's go ahead and focus on the bottom number first. Now, the examples that they give us, all of the bottom numbers are 1. Let's highlight that. And they all do have 1 proton on the inside. Therefore, the bottom number tells us how many protons each. So this one here, bottom number of 3, lithium has 3 protons. Could be A, it could be B, but we'll get rid of these 2 here. Next, what does the 7 tell us? So we know what the bottom number is, the number of protons, but what about the top one? Maybe that's the number of neutrons. Well, for the first one, that can't be right because 1, it doesn't actually have 1 neutron here. And this one doesn't have 2 neutrons, so that doesn't seem right. But maybe it's telling us how many things are on the inside or the nucleus. 1 thing here, 2 things here, and 3 things here. It's basically all of the stuff on the inside added together. So if we add the protons and the neutrons, that does give us the top number, 3 in this case here. So that's it. The top number tells us if we add the protons and the neutrons, then it should give us this top number. But these 2 add to 6 for option A, so it's not the first one. But then B, adding 3 protons, 4 neutrons, the stuff on the inside, those do add to 7. And that's our correct top number. So B, these are the properties that the specific isotope of lithium will have here. And if you're a visual learner like me, we'll go ahead and draw this out. So again, if it's written this way, the bottom number, the number of protons, 3 of those, also has 3 electrons. But then the top number, everything in the nucleus added, 1, 2, 3, 4, 5, 6, 7, that checks out as well. So these numbers definitely work, and that's how we can apply the concept that they gave us here. For this one, we've got a diagram, and they're going to explain it, so let's see. When uranium-235 undergoes nuclear fission, it absorbs a neutron, splits into smaller nuclei, and releases energy and neutrons. So what's happening here? Well, this diagram is showing us the process of nuclear fission. Looks like it's taking something and splitting it apart. We're starting with uranium-235. The first thing it does is it absorbs a neutron. So this thing here has to be a neutron. Then it's going to split into smaller nuclei, these two things here. But finally, that's going to release energy. Let's highlight that. So this here in the diagram looks like energy being released. And finally, it's also going to release neutrons at the end. Therefore, these 3 things here are neutrons being released. Okay, once we have the main idea, then we can see which answer describes this process. Why might uranium-235 cause a chain reaction? So why might this element here eventually cause a chain reaction? And a chain reaction, that's just a process that repeats over and over again. So how might that happen for this diagram? The first one, the extra protons attract more neutrons. Well, they don't say anything about extra protons popping out, so if they don't mention it and we don't see it in the diagram, that's probably not right. Let's get rid of that one. The next one, the smaller nuclei contain more energy than uranium-235. Do we have more energy here? Well, we know that there was energy that was released right here, but we don't know that there's more energy in this case, just that the energy was released. So again, we're not quite sure about that either. Let's get rid of that. The third one, the released neutrons. Do we have those? Well, we definitely do. We've got 3 released neutrons at the end here, so that checks out. Those can strike other uranium-235 atoms, causing them to split. Is it possible that these strike other uranium-235 atoms? Well, let's say that there's one right here. One of these neutrons could get absorbed by it, and that actually would start the process all over again. It would get absorbed, then it would split in 2, release 3 neutrons. And if there's another uranium atom floating around, it could absorb another released neutron, start that process all over. So this could definitely happen based on the diagram and the information. So there's definitely evidence to support C, and this is the correct option here. Because the last one, the reaction releases extra electrons. Once again, we don't know that there's extra electrons anywhere, so that doesn't sound right either. But one thing that these incorrect options have in common is they all contain these words to be aware of. So on multiple choice tests, be careful when you see words like always, never, more, less, or extra. Those are usually the incorrect options. So this can be a strategy to help eliminate options. When they give you a passage to read, start with the question first, and that can help us figure out what to pay attention to. What prevents the sun from collapsing under its own gravity? So what prevents the sun from collapsing? And specifically, we want to see if they mention gravity here. Nuclear fusion, in which hydrogen fuses into helium, occurs continuously in the sun. This process balances the inward pull of gravity, there it is right there, with the outward push of energy from the core. Let's break this down. They talk about some process balancing, and the process they mention is in the first part, nuclear fusion. That's providing the balance here of the inward pull of gravity with the outward push of energy from the core. All right, a lot going on, Basically, nuclear fusion, it's providing a balance, so the sun doesn't collapse in its own gravity, but has an outward push of energy to prevent that. And that process is nuclear fusion. So this is the main thing we want to look for in the answer so far. But let's keep reading. If fusion stopped, gravity would cause the sun to contract, or to shrink, raising pressure and temperature until fusion resumed or the sun collapsed further. Well, we still have all the main information here, so let's look for any of these key phrases or words to show up. The first one, the rotation of the sun's outer layers. Is that preventing the sun from collapsing? Well, they don't mention rotation anywhere, and they don't mention outer layers as well. So if they don't mention it, probably not the right one. The next one, the fusion of helium into hydrogen. But here we go. They mentioned fusion, that's one thing we were looking for. And they mention helium converting into hydrogen. They say something like that up here. But if we look really carefully, they say that hydrogen fuses into helium, so hydrogen becomes helium. But down here they say the opposite. They say that helium turns into hydrogen. So they're being really tricky by using a phrase and then reversing it in the answer. So super tricky trying to get us to choose that, but that's actually not quite right. The third one, the release of energy created by fusion. This is a great option, once again mention fusion, but they also use one of the key phrases, the release of energy created by fusion. And we know that this process of fusion creates an outward push of energy, same thing as a release of energy to prevent the sun from collapsing with gravity. So C, this has a couple of the correct phrases and words we were looking for, and that is the correct option. Because the last one, the pull of gravity from planets, is that preventing the sun from collapsing? Once again, they don't mention the pull of gravity from other planets, so they don't mention it, probably not the right one. And this is really common, where the first and the last one mention things that they didn't talk about, so we could eliminate those, and we're between two options. Then we just need to read carefully and see if they're intentionally trying to mess up some phrase to make us choose that one. So by reading really carefully, we can see fusion is the correct process that releases energy, preventing the sun from collapsing under its own gravity here. What is the atomic weight of chlorine? Let's go ahead and read, see if they describe how to find atomic weight. Atomic weight is the weighted average mass of all naturally occurring isotopes of an element. So let's pause. They talk about atomic weight being the weighted average mass. Well, what is this? Well, normally to find an average or a mean, you just add all the things that you're given, the mass in this case, and we have two of them. To find the average, you would just add these together, get a total, and divide by 2 since you have two things. But this is different because it's a weighted average, so it's going to be a different process. And this is something you'll have to memorize ahead of time, so let's check it out. To find a weighted average, you want to multiply each value, the masses in this case, by the percent of the time that they show up. Because this mass occurs 76% of the time, we want to multiply both of these together here. So let's copy that down. Then this mass occurs 24% of the time. Let's go ahead and multiply these together. Let's copy that. And finally, we want to add the values together. So we'll put a plus between those. But we can type this into the exact calculator that they'll give you on the test, and it's this one here. So let's go ahead and do it. We've got these two multiplied, 34.97 times 76%. Just go ahead and type 76, and the percent is right here. Just use the green button and then that one to get the percent sign to show up. Okay, keep going. Plus, then we've got 36.97. And that one shows up 24% of the time, so multiply that by 24. Again, second this button to get the percent, and we're good. Go ahead and hit enter. So this is the final answer, 35.45 That is the atomic weight of chlorine here. So as long as you know the process for a weighted average, you could easily find them for a table like this. And by the way, if they gave you 3 masses with different percentages, we would just multiply each of those and then add all 3 together. So that's how you could do any weighted average. They may give you a diagram like this and ask you to find the correct chemical formula that represents it. A diagram for a chemical reaction is drawn out above. Match this diagram with its correct chemical formula down below. To start, on the left side we have 4 H's. These might be hydrogens. So we might think, okay, this has 4 H's and this has 4 H's. These might be correct here. But this is where you need some background, because if they write 4H like this, it's actually 4 separate hydrogens. But ours are connected with a bond. So it's going to be different. It's not going to be B or D here. Whenever you have 2 of the same letter connected, they're going to write that letter with a little 2. That means that they're connected or bonded. And same thing here. We've got 2 of the same letter. They're connected, write it with a little 2. But as we can see, the answers also have this big 2 in front. That just means we have 2 separate ones. We've got one here and one here. So we do in fact have 2 separate molecules of H2. And by the way, a molecule is any time things are connected. So this is a molecule, this is a molecule, or these 3 represent a molecule as well. All right, let's move to the middle. We've got 2 O's. Are we going to write it with a little 2 or a big 2? Well, you already know it's going to have a little 2 since they're connected. And by the way, don't worry about this if it's got 2 lines or 1 line. This is a single bond, this is a double bond, but it doesn't affect the number here. So we know this is going to be a little 2 with that connection going on, because 2 in front means 2 separate oxygens. So C, that's not correct. But there we have it. A, that's got all the right stuff so far on the left side, and that's all we needed to find out to match it with the correct chemical formula. Because the last part, do we have 2 H2Os here? Definitely, because this is one H2O or water molecule. It's got 2 hydrogens, 1 oxygen. They mush all the letters since they're connected together. And same thing here. So we have 2 separate ones. That's why the big 2's in front. So it all makes sense there. Here they're going to teach us about half-life. Let's just go ahead and read it first this time. Half-life is the amount of time it takes for half of a radioactive substance to decay. So half-life, it's the amount of time for half of something to decay, or basically to disappear. Okay. This process happens at a constant rate, meaning that no matter how much of the substance you start with, the same fraction decays during each lifetime. This sounds important as well. The same fraction decays or disappears during each half-life. Finally, scientists use half-life to determine the age of materials, such as fossils or rocks, through techniques like radiometric dating. The question: a sample of radioactive isotope has a half-life of 10 years. And if something has a half-life of 10 years, that means that half of it is going to decay or disappear 10 years later. Therefore, if you start with 100 grams, how many grams will remain after 20 years? So we're starting with 100 grams. We want to know how much after 20 years. To start, let's take our initial amount of 100 grams and see what happens. It's got a half-life of 10 years, so we know 10 years later that half of this is going to be left over. Half of 100 is going to be 50, just divide it by 2. But eventually we want to find how much remains after 20 years. So let's put that. But notice, this is just an additional 10 years, and 10 years is the half-life. So in an additional 10 years, half of it is also going to disappear. The same fraction decays during each half-life. So half of 50 gets us to 25 grams. So that's it. From start to finish, we went 10 years, it got cut in half. We went another 10 years, it got cut in half again. So 20 years later, we've got 25 grams available. So final answer there. So even if they don't give you this exact question, knowing what half-life is provides some background if you see another question about it, like this last one here. This time the question is, why might different elements be used for radiometric dating? Well, they mentioned radiometric dating in the last sentence right here. Let's highlight that. So let's go ahead and read the last sentence and figure out why it's used. Scientists use half-life to determine the age of materials. There it is. It's being used to determine the age of things, like fossils or rocks, through techniques like radiometric dating. So basically, this technique is used to determine the age of things, like fossils. Okay, why might different elements be used to do this process? Let's see. Now, because radiometric dating is used to determine the age of materials, let's see if they mention anywhere in the answers about ages or timelines of things. The first one, an element's half-life determines the time range it can best date. In other words, each element, it's going to be used to determine a certain time range here. Same thing as the age of something. So this definitely seems to work so far. Let's see if we can eliminate any other options. B, some elements change their half-life depending on temperature. They don't say anything about temperature though, so it's probably not that one. The third one, metals are more reliable than gases for radiometric dating. But remember, when you see a word like more, that's probably an incorrect option here. And specifically, they don't mention anything about metals or gases, so we don't have enough information to say if that's true. But the last one, only heavy elements decay into stable forms. Well, it could be true based on logic, but again, we don't have evidence to support it in the passage. So a word like only is also a distractor one. That's not it either. So we know it's A, but why might different elements be used for this process? Well, if you're dating something like a fossil, a dinosaur fossil would be millions of years old, so you may need something with millions of years for its half-life. But if you're dating something like a mummy or human remains, you just need thousands of years to do that, so a different time range in other words. And a half-life of 10 years might be helpful for something that died in the last 100 years, like a tree for instance. And because different elements might have different half-lives, that can help us determine the time range that it can best date most accurately. So A definitely seems to make the most sense. Check out my website for practice problems just like these ones and others as well. And here's another science video on chemical equations for practice with those. Let me know what questions you have, what else you want me to cover. Good luck, you got these. We'll see you in the next video. Toodles.